Thank you very much for this introduction and for this invitation to speak. So in this presentation, I will focus on the last report that we have released regarding the physical science basics of climate change. And this is part of a set of scientific assessment reports, 3 special reports released in 2018 and 2019 on global warming of 1.5 degrees Celsius, on the ocean and cryosphere in a changing climate, and how to enhance our resilience facing these through components of climate change and land with a lens on the food system. Our report was released last summer. I'll explain the preparation mechanisms, the key findings, and an analysis of the barriers and obstacles to the contribution of female scientists. By the end of this month, there will be the release of the Working Group 2 report on vulnerabilities, impacts, and adaptation options. And by beginning of April, the Working Group 3 report on mitigation, so how to ensure sustainable development while reducing greenhouse gas emissions. Each report is what I describe a co-construction. First, we listen to the representatives of all governments in plenary sessions for the themes they want to be considered. Then we have a 1-week brainstorming with about 100 scientists to define the structure of the report and keywords for each chapters. There's a call for scientists to contribute. For our main report, we received typically 1,000 nominations. Myself, my fellow co-chair, Palma Ojai from China, and the 7 vice chairs of our working group, we select the authors based on their expertise, primarily, with attention to the regional balance and gender, because having a diverse group of authors is critical to avoid community biases and sharpen the quality of the assessment. The report is made from assessing scientific evidence from the peer review literature, observations, process understanding, global and regional climate model results, insights from past climates. So the authors develop a first draft, it goes under expert review, they develop a second draft, and then it goes for expert and government review, and it includes the first draft of the summary for policymakers. It's reviewed again, the chapters are consolidated for a main report, it's about 3,000 pages, a 100-page technical summary, and a 25 pages summary for decision makers. That one goes under government review with experts from governments. It's revised by the scientists, and then it's approved word by word by representatives of all governments. And this makes our reports an agreed common scientific basis, and it allows to separate that body of evidence from international climate negotiations. The principles are to deliver a rigorous, exhaustive, and robust assessment in a way that is policy relevant. So we're not writing a textbook or an encyclopedia. We focus on what's policy relevant in a way that is neutral and non-prescriptive. Just to give you a sense of the Working Group 1 report on the physical science basis, it's 3 years of work, an involvement of about 30% to 50% of time from the 233 scientists from 65 countries who have assessed evidence from 14,000 scientific publications and have received 78,000 review comments from 1,890 individual reviewers and 46 countries, half from the global north and half from the global south. And the size of the challenges has increased due to the pandemic. So we had to shift to online work at about 2/3 of the process. For the first time last summer, we organized a virtual approval session with representatives from all governments, up to 700 participants. And that represents about 186 hours of Zoom calls during 2 weeks. That approval allows to ensure a super strict quality control of the assessment. It allows to develop a balanced summary that addresses the needs indicated by all governments, grounded in the main assessment, and a clear presentation of the facts. So all the report is available online if you want to dive into it. And you can also find frequently asked questions as outreach material, 2-page summaries of the main findings for regions, or an interactive atlas, which is compliant with our approach to open data and open access to the information assessed in our report. So I'm going to dive into the main findings before sharing some thoughts about barriers to the participation of women scientists. So the first thing is human influence on climate is now an established fact, unequivocal. It is a fact that human activities drive recent and fast increases in greenhouse gas concentrations in the atmosphere. You see the rise since 1850, which leads to much higher levels than any time in the pre-industrial period or the last 800,000 years. For CO2, it's driven by fossil fuel combustion, deforestation. For methane, the most recent rise is driven by livestock and by fossil fuel leakages. For nitrous oxide, it's driven by the use of fertilizers and industrial processes. It's also a fact that because we add greenhouse gases in the atmosphere, we cause a radiative forcing that alters the radiative balance of the Earth. Of course, we look at natural drivers, the small cycles due to solar activity, the episodic occurrence of major volcanic eruptions that have a temporary umbrella effect, a cooling effect during 1-2 years due to particles in the high atmosphere. But if we look at the Earth's radiative budget, it is increasingly dominated by the heat trapping effect of greenhouse gas concentrations that was partly offset by the cooling effect from pollution particles. And that cooling effect has peaked about 10-20 years ago, thanks to air pollution controls in North America and Europe. It's still increasing in some regions. But you can see that in the last decade, we've lost a bit of that umbrella masking effect. So the two main drivers have worked in the same direction: less cooling effect from aerosols, more warming effect from greenhouse gases. So the rate of change in our perturbation on the climate system has increased. Because we trap heat due to the increase of greenhouse gases in the atmosphere, it's causing a heating of the climate system. Most of the excess heat goes in the ocean. It plays the role of an accumulator. It's limiting warming at the Earth's surface, but it makes climate change irreversible due to the hundreds of years of timescale of global ocean mixing. Changes are widespread in the atmosphere, warmer, wetter, with changes in circulation, a general retreat of the cryosphere, thawing of permafrost, reduced spring snow cover, less Arctic sea ice, generalized melting of glaciers, and a gradual increase in the melting of the Greenland ice sheet and the faster flow of sectors of the Antarctic ice sheet. Over land, changes in growing season, an increase in greenness as seen from space, intensified precipitation at the global scale with strong regional contrasts, species shifts, and an ocean that's warmer, that's acidifying, taking up 23% of the CO2 emissions, also with shifts of species and a loss of oxygen. These changes are also unprecedented. Over more than 1,000 years for the loss of sea ice, 2,000 years for the loss of glaciers, 11,000 years for the warming of the sea surface, an unprecedented rise of sea level over more than 3,000 years, and ocean acidification is unusual in more than 2 million years. If we focus on one of the key indicators of the state of climate, the increase of temperature at the surface of the Earth, over land and over the ocean, you can see that each of the last decades has successively been the warmest, For the last decade, the warming level is reaching 1.1 degrees Celsius above the late 19th century. And that warming is unprecedented in more than 2,000 years. When we assess the role of natural drivers or human influence, we rely on two methods. The first one is the result of global climate simulations with natural drivers, large ensemble of simulations to explore climate variability, natural climate variability, and then the response to greenhouse gases and aerosol cooling. And the outcome of this assessment is that our best estimate is 100% of the observed warming to date is due to human influence, with the warming effect of greenhouse gases partly masked by the cooling effect from aerosol cooling. And none of the natural drivers can explain the centennial trend. They play a role at the regional scale over decades, but they can't explain the heating of the climate system. We have another approach, which is to calculate the radiative forcing effect of each driver and then assess the climate response. These two approaches are fully consistent and they show a dominant role of carbon dioxide, which has a specific cumulative effect on climate, and the second dominant role of methane emissions due to its powerful greenhouse gas effect on the short term and its indirect effect on the formation of ozone in the low atmosphere. That ozone is a greenhouse gas and an air pollutant as well. So there's a double effect for methane. If we look at the outcome of these attribution studies, so looking at causes and consequences in the complex climate system, the picture is really clear, with human influence the main driver of many changes. And as you can see, the level of confidence is stronger for aspects related to energy, and the level of confidence is always a bit lower for aspects related to hydrological changes or dynamical changes, where there's a superposition of natural variability and human influence on the climate system. Climate change, it's already affecting every region on Earth. There's an intensification of hot extremes in every region. Each hexagon is a region, like WCE is West Central Europe, or Southern East Asia is SEA, so that you can understand that's a global map that's simplified. So every hexagon that's red is where there's an intensification of hot extremes, and the dots show the level of confidence in the attribution of that intensification to human influence. This is really widespread. When you look at extreme rainfall, every hexagon that appears in green is where there's an intensification of precipitation in extremes in terms of frequency and intensity. There's a widespread signal, but our knowledge is limited by the lack of access to daily data back to the 1950s, or to the lack of attribution studies in many countries, especially in Africa or South America. And it also reflects the imbalance in the distribution of the physical climate research community. The level of confidence is highest for Northern Europe here. Regarding agricultural droughts, those related to soil moistures, everywhere in yellow is where there's a discernible increase in the intensity of droughts. And you can see that the confidence is strongest around California and the Mediterranean region on the key role of human influence on climate, intensifying these droughts. Let's now look at the future. And for that, we explore a broad range of illustrative scenarios associated with greenhouse gas, air pollution, land use changes. It's illustrated here for carbon dioxide because it plays a dominant role. We explore scenarios where emissions stay close to today's levels during a few decades before a gradual slowdown, increase very strongly, decrease or decrease very strongly. The scenarios with very high emissions are considered to be less plausible because of climate policies that are in place and technological advances, for instance, to produce low carbon electricity at reasonable costs. The low or very low emission scenarios would imply much more climate ambition and effective action that is currently on the table. And the outcomes of the last climate negotiations last fall, if all the pledges would be implemented, they could imply a very small decrease between emissions of the last decades and those by 2030, not a strong decrease as indicated by these scenarios, leading to reach net zero CO2 emissions by 2050 or 2070. And there are a number of regions in the world where there have been pledges to reach these zero emissions at different times between these two time horizons. We had major advances in basic climate research to quantify the global climate response. Equilibrium climate sensitivity measures the outcome of all climate feedbacks that drive the increase in surface temperature at the global scale after doubling the concentration of CO2 from pre-industrial levels over a few centuries. And as you can see, the first report from a US Academy of Science report by the late 1970s had a best estimate of around 3 degrees and a broad range. And we've stayed with these ranges for decades, but recently through progresses in climate science to combine evidence from process understanding, instrumental constraints, insights from past climates, and the ability to track processes that lead to difference in the future to things that are observable today so that we can use information to constrain the outcomes. This has led to a best estimate that's still at 3 degrees, but with a much narrower likely range for climate sensitivity. So for each scenario, we have a smaller uncertainty of the climate response. I want to flag that the Nobel Physics Prize last year was awarded to climate scientists who have played a key role in theoretical understanding and numerical modeling of the climate system, Suki Manabe, and methods to attribute warming to drivers, Klaus Hasselmann. So let's look at the climate response to these contrasted scenarios. And a strong message is that in the near term, we expect warming to continue and exceed a level of warming of 1.5 by around the 2030s. This is due to, even in the most ambitious scenarios, less pollution particles and still, but declining CO2 emissions that continue to increase the cumulative total CO2 emissions. If emissions stay close to today's levels, then the level of global warming could surpass 2 degrees in the 2050s. Limiting warming well below 2 degrees or close to 1.5 degrees, these are the targets of the International Paris Agreement. So it shows that these targets cannot be met unless there are strong declines in global greenhouse gas emissions in the coming decades. Why every increment of warming matters? Because mean changes in temperature in every region scale to the level of global warming. It's illustrated here with larger warming over land, much stronger warming in the Arctic than the global average. Changes in the water cycle are also directly related to the level of warming. A thermodynamical effect, milder and wetter conditions in cold regions, more precipitation there, and a dynamical effect, shifts in atmospheric circulation, leading to a decrease in annual mean precipitation in areas with semi-arid or Mediterranean type climates. And that increases with the level of warming. Changes in annual mean soil moisture, they reflect the change in precipitation and the evaporative demand by the atmosphere. So more evaporation, more transpiration with warmer conditions. And a drying of soils in areas like Central America, South Africa, areas of Australia, around the Mediterranean, or the Amazon is already observed, and it's expected to increase with every fraction of additional warming. A main finding from this report is that more warming implies an intensification of the water cycle, of its variability from season to season, year to year, with more severe wet and dry events, and an intensification of global monsoon precipitation. At the regional scale, monsoons are sensitive to the wettening effect of greenhouse gases and the drying effects of regional pollution particles, so they can have contrasted influences. With any further increment of warming, there will be an increase in the frequency and intensity of hot extremes and marine heat waves. Events that occurred only once per 50 years by the end of the 19th century are already 5 times more frequent. They would be 9 times more frequent for a level of warming of 1.5 and 14 times for a level of warming of 2 degrees. For heavy precipitation events, the Clausius-Clapeyron relationship really applies, and even for the extreme precipitation events, their intensity can increase by 7% per degree of global warming. It's also the case for severe droughts in areas with decline rainfall shown previously. Many other changes directly scale to the level of warming for fast responding aspects like Arctic sea ice or snow cover or permafrost. So a strong message is we need to prepare better and use that knowledge to prepare and anticipate in disaster planning, in adaptation strategies, for events with larger magnitudes, more frequent events affecting new locations at different timings, and new combined events such as fire weather, increasing with dry and hot conditions, or compound flooding due to sea level rise and heavy precipitation over land. For some aspects, we can't go back. Glaciers will adjust over decades to centuries to current warming. The ocean will continue to warm at depths over hundreds of years, and the Greenland and Antarctic ice sheets have timescales of hundreds to thousands of years. So sea level will continue to rise, but the rate and the magnitude will depend on our greenhouse gas emissions. It was asked to us to also assess deep uncertainty associated, for instance, to ice sheet instability processes. So we've done that with storylines. We don't know what is the threshold associated with the triggering of dynamical instability of sectors of the Antarctic ice sheet. We don't know which level of warming or which time horizon could be related to that. But what we can quantify is if this instability is triggered, then from a physical basis, what could be the maximum contribution to sea level rise? And that's indicated with a dashed line as a way to communicate an unknown likelihood or low likelihood possibility that would have major implications for global coastlines. And of course, global sea level rise doesn't stop by the end of the century. We need to be prepared for a continued rise, more than 1 meter in the case of low CO2 emissions, several meters in the case of intermediate or very high emissions. And if peak warming is at around 2 degrees Celsius, we need to prepare for 2 to 6 meters increase over 2,000 years, and more than that for higher levels of peak warming. So it gives a sense of the very long-term commitment of our emissions in the coming decades. We also alter the global carbon cycle in a major way. Today, the ocean and land absorb about 54% of our emissions. But with high warming, their efficiency can be reduced. Saturation of the absorption of carbon in a warmer ocean, dieback of forests, permafrost thaw, this can alter the relative efficiency of the natural sinks, but mostly for high levels of warming, typically above 2 degrees Celsius after 2050. It also stresses the importance of restoring and preserving the ecosystems over land and in the ocean. In our report, you'll find the characteristics of climate change in every region and the link with the level of warming. So we look at 33 conditions of the physical climate, gradual trends, extremes, indices of variables associated with known tolerance thresholds, and how they change in different regions. If the level of warming reaches 2 degrees by 2050, for most of the world's land regions, they'll face 10 concurrent changes, and for 50%, 15 concurrent changes. So it really matters to use that information, assess exposure, vulnerability, and anticipate, use that climate science knowledge to be able to reduce related risks. You can find that in our report in the interactive atlas. So we only provide the characteristics of regional climate change, but we don't go to the impacts. That's not part of our direct assessment. And one example is shown here. It is for the number of days where peak temperature goes above 35 degrees Celsius. It is a heat warning index because it's associated with a decline in maize crop yields today. So you can see that for low levels of warming, there's an increase in the number of days with this level of warming, first in the tropics, and for higher levels of warming, a strong increase as well in mid-latitudes, with the likelihood of increasingly affecting food security through impacts on key food producing areas. I want to flag that women are particularly sensitive and vulnerable to some aspects. Women involved in agricultural activities and their land rights. Regarding consequences of extreme rainfall and sea level rise, many women and girls in the world don't know how to swim. So in the case of a major event, they can be more vulnerable to these hazards. Finally, some changes can be slowed. Sea level rise can be slowed, giving more time to adaptation strategies on coastlines. And everything that directly depends on the level of global warming, their changes can be stopped if we manage to limit global warming. So from a physical science basis, what does it take? The first main message is that there's a cumulative effect of CO2 emissions. It is the outcome of complex, nonlinear processes that offset each other. The fact that radiative forcing of CO2 does not increase when you have more CO2 emitted, the gradual increase is slower, but the fact that a warmer ocean has less ability to store heat and carbon. It's basically the offset between these two mechanisms that is behind that linear relationship between the total amount of CO2 emissions due to human activities and the level of warming. So it implies that limiting warming is associated with a remaining carbon budget. The remaining carbon budget for 1.5 degree of warming is about with 2/3 of chance of success. It's around 400 gigatons of CO2. That's about 10 times the level of annual emissions now. So it gives a sense of the very small margin that is associated with limiting warming at such low levels. Let's look at the effect of one pulse of today's emissions on global surface temperature. And you can see that over 100 years, it's dominated by CO2. So reaching net zero CO2 emissions, it's a key condition to limit long-term warming. And when it's reached, there's no much more warming that would occur in our estimate. When you look at the effect of 1 year of emissions now, over 10 years, you can see that there's an effect of CO2. It's offset by the cooling effects of pollution particles and amplified by the near-term warming effect of methane emissions. So if we want to limit warming in the near term, it is really critical to reduce methane emissions, and that can have a very quick effect on atmospheric composition, this effect on climate and air quality through the formation of ozone. If there are sharp declines in CO2 emissions and other greenhouse gas emissions, the effect on atmospheric composition could be seen within a few years. But the effects on global surface temperature, due to the amount of year-to-year variability, could be observed over about 20 years. So it also gives a sense of the time shift between action and discernible benefits. I think this presentation shows really clearly how much the climate we experience in the future depends on our decisions now, but also how much the climate-related risks in the future depend on our ability to use knowledge about future changes to take that into account in today's decisions, so as to define choices that are resilient in the face of a changing climate. Our decisions now also have other implications, and I would like to put an emphasis on the participation of women scientists. It matters to have a fair representation of the scientific community and the contributions of women scientists. It's critical to have a diversity of expertise and perspectives. There's a strong gender dimension of climate-related risks. I've mentioned some of them, but also of climate-related responses. And allowing women scientists to participate to international science assessments is also an international recognition. It's positive for academic repute, and it gives a voice for women scientists at the science policy interface. This is the outcome of a survey conducted over authors of the recent IPCC reports with more than 500 respondents. When we look at the contribution of women to IPCC reports since the 1990s, you can see a sign of progress. Today, about 30% of the authors of reports are women scientists. It's about the same proportion that is seen in research communities worldwide, but with a glass ceiling effects and often lower representation at senior levels. Over the whole IPCC history, there have only been 3 female co-chairs, including 2 now. So it shows that progress has been particularly slow at leadership positions. If we look at the participation across the various working groups, we see that there are fewer female authors in the physical science basis. We received the same percentage in the nominations than we have in this selection that I contributed to shape. There are barriers for women in climate sciences as in other disciplines. In some regions of the world, access to training and funding. In many regions, access to promotions and citations, limited role models, unequal family responsibilities, and fewer recognition through awards or leadership positions. And it's striking to look at a Reuters 2021 ranking of the world's top 1,000 leading climate scientists based on citation analysis. Only 12% were women and only 2 in the top 50. There are unequal barriers for nominations of female scientists to be selected to write IPCC reports. They also reflect biases in organizations and representatives of countries at play or scientific organizations. Sometimes limited access to that call for participation, and also reluctance from women to put themselves forward, also reflecting a lack of confidence, in addition to obligations to families, limiting, for instance, the ability to travel. We have the outcomes of that broad gender survey. And a few striking points are, for instance, that women were 15% less likely than men to agree that everyone had equal opportunity to be nominated, shape contents, lead chapters. More women than men have observed someone taking credit for a woman's idea, seeing a woman being ignored or being patronized. When I supervised the report, we faced challenges. We monitored them through regular surveys after each meeting. We worked with consultants to implement guidance for everyone on inclusive and participatory work approaches. And I think it really helped to be sensitive to these issues. So that group, analyzing the gender dimension of contributors to IPCC reports, has identified 6 priorities: monitoring gender balance in nominations, share best practices. We have already implemented a gender action team to make clear monitoring, reporting, and actions within the IPCC leadership. There are concerns about increasing the share of women in the leadership and mainstreaming that dimension in choices, providing training on inclusive practices and approaches leading to the management of reaching consensus amongst group of authors, monitoring the situation and also ensuring that the work to develop such international assessments can take better account family challenges, including enhanced support for remote participation. And I think that might be a positive outcome of the shifts to online work that we have faced in the past years. Thank you for your attention.